This is Physics 2120, Lecture 20, and today we're going to talk about LC circuits and RLC circuits. So an LC circuit is a capacitor connected to an inductor where we have a switch, where we can have a capacitor charged at one point and we close the switch to see what happens in the circuit. We're going to assume here that there's no energy loss due to radiation or that there's no resistance in the wires. Now, under those conditions, the current in the circuit and the charge on the capacitor oscillate between maximum positive and negative values. With zero resistance, no energy is transformed into internal energy, and those oscillations would persist indefinitely. Those idealizations are that there are no resistance and no radiation. So the capacitor is fully charged to start. The energy in the capacitor is stored in the electric field of the capacitor. And the energy in the capacitor is Q max squared over 2C. And the current in the circuit is 0, and so there's no energy in the inductor. Now, we close the switch. The current is equal to the rate at which the charge changes on the capacitor. So as the capacitor discharges, the energy stored in the electric field will decrease. But now there's some current, and so some energy is going to be stored in the magnetic field of the inductor. So energy is transferred from the electric field to the magnetic field. Eventually, the capacitor becomes fully discharged. It means it stores no energy. All of the energy is then stored in the magnetic field of the inductor, and the current is at its maximum value. The current is now going to decrease in magnitude, recharging the capacitor with the plates having opposite the initial polarity. Eventually, the capacitor becomes fully charged again and the cycle repeats. The energy continues to oscillate between the inductor and the capacitor. The total energy stored in the LC circuit remains constant in time and is just equal to the energies in both the capacitor and the inductor, which is going to be Q squared over 2C plus 1/2 Li squared. Now this is analogous to a mass spring system, where the potential energy, 1/2 kx squared, stored in the spring, it's analogous to the potential energy, 1/2 CV squared, stored in the capacitor. All of the energy is stored at the capacitor at t equals 0. That's the same as the spring being stretched to some amplitude. So, as the mass moves forward, the kinetic energy of the spring increases, and that's analogous to the magnetic energy, the 1/2 Li squared, stored in the inductor. And at 1/2 the total, or 1/4 of the total period, all of the energy is stored in the magnetic energy in the inductor. Same as the mass as it passes through the equilibrium point. There's no energy stored in the spring, it's all stored in the kinetic energy of the mass. Now, if we continue to look at 1/2 the period, the energy of the circuit is completely stored in the capacitor again with opposite polarity. That's analogous to the spring being stretched to minus the amplitude. And as it comes back, at t equals 3/4 of the total period, the energy again is completely stored in the magnetic field in the inductor, or the mass again reaching its equilibrium position and all the energy stored in the kinetic energy. And eventually, when the cycle is complete, the conditions return to those identical to the initial conditions. At other points in the cycle, energy is always shared between the electric and magnetic fields, or in the mass spring between the kinetic energy and the potential energy in the spring. So in an LC circuit, charge can be expressed as a function of time. The charge on the capacitor is the maximum charge times cosine omega t plus phi. This is for an ideal LC circuit. And the angular frequency omega of the circuit depends on the inductance and the capacitance. It's called the natural frequency of oscillation of the circuit. And omega for this circuit is 1 over the square root of LC. The current then we can express as a function of time as the derivative of the charge. So that's going to be minus omega Q max sine omega t plus phi. Then the total energy can be expressed as functions of time. the total energy is Q max squared over 2C cosine omega t squared plus 1/2 L I max squared sine omega t squared. So the charge on the capacitor oscillates between a maximum value and a minimum value. And then the current in the inductor oscillates between I max and negative I max. And notice that the charge and the current reach maximums 90 degrees out of phase with each other. So in other words, when Q is at a maximum, I is 0, and so back and forth. If we were to plot the energy of both the capacitor and the inductor, we see that they oscillate also. And that at t equals 0, all the energy is in the capacitor, none is in the inductor, and they go back and forth. So it's all in the inductor and nothing in the capacitor. So when the total energy is stored in one field, the energy in the other field is 0. Now, in actual circuits, there's always going to be some resistance. So therefore, some of the energy is transformed into internal energy. And radiation is also inevitable in this type of circuit. So the total energy in this circuit is continuously decreasing as a result of those two processes. Let's look at an example problem, an LC circuit oscillation problem. So I have a capacitor in a circuit shown as charged when switch 1 is open and switch 2 is closed. Switch 2 is then open, and when switch 1 is closed, we have an LC circuit. Find the frequency of oscillation of the circuit, and what's the maximum charge on the capacitor and the maximum current in the inductor, and what are the charge and current as functions of time. So we begin finding the frequency. We know that frequency is the angular frequency over 2 pi, and omega is 1 over the square root of LC. So the frequency is going to be 1 over 2 pi times the square root of LC. We plug in the values of the inductor and the capacitance given in the figure, and we get 1 times 10 to the 6 hertz, or 1 megahertz. So in other words, when switch 2 is open and switch 1 is closed, the current is going to oscillate back and forth 1,000,000 times per second in this circuit. The maximum charge on the capacitor is just CV, which, given our value of capacitance and the voltage of 12 volts, we get 1 times 10 to the minus 10 coulombs. The maximum current from our equations before is just omega Q max. So omega is 2 pi times 10 to the 6 hertz times our maximum charge that we determined. So the maximum current is going to be 6.79 times 10 to the minus 4 amps. Now, given these, we can find our charge as a function of time. The charge goes as cosine omega t, so it's just our maximum charge, 1.08 times 10 to the minus 10 coulombs, times cosine 2 pi times 10 to the 6 hertz, times time. And then I as a function of time is going to be minus I max sine omega t, which we know what all those are, and we can plug it in and get the functional form of both charge and current. So now what happens if we don't ignore all resistance and we just consider a circuit that has resistance in it? So if I have a circuit that contains a resistor, an inductor, and a capacitor, in this case in series, it's called an RLC circuit. And we're going to assume the resistor represents the total resistance of the entire circuit at this point. The total energy is not constant, since there is a transformation to internal energy in the resistor at a rate du dt is minus I squared R. We're going to ignore radiation losses still. And that's the case, then the circuit's operation can be expressed as minus L di dt minus Ri minus Q over C is equal to 0. This is just looking at Kirchhoff's laws as we go around the circuit. We know that di dt is actually the second derivative of charge with respect to time, multiplying through by a minus 1, and we get this differential equation here. So if I want to understand it, I need to solve this differential equation. The RLC circuit is analogous to the damped harmonic oscillator. So when R equals 0, the circuit reduces to an LC circuit and is equivalent to no damping in a mechanical oscillator, so a spring going back and forth. When R is small, the RLC circuit is the same as a lightly damped mechanical oscillator. I'm not going to go through the solution to the differential equation, but charge is some maximum value times cosine omega dt, where omega d is going to be the frequency of damped oscillation, and we have an exponential term out front. So omega d is the angular frequency of oscillation for this damped circuit, and it's the square root of 1 over LC minus R over 2L squared. Notice that as R goes to 0, that the frequency is exactly the natural frequency of oscillation we talked about before. When R is very large, the oscillations damp out very rapidly. In fact, there's a critical value of R above which no oscillations occur. And that critical value is the square root of 4L over C. If R is equal to RC, the circuit is said to be critically damped. When it's greater than RC, the circuit is overdamped. So this graph shows an underdamped oscillation. The maximum value of Q decreases after each oscillation, and this is analogous again to the amplitude of a damped mass spring system, where the charge is going to oscillate and get smaller and smaller amount each time as the resistor pulls energy out of the system. This graph shows an overdamped RLC circuit, where the oscillations damp out rapidly, and so I get a maximum value of charge, and then it just rapidly goes down to 0 and does not oscillate at all. So that lets us look at the analogies between electrical and mechanical systems. A one-dimensional mechanical system and electrical circuit have a relationship to each other. And if we can think of charge as position, then current, which is the derivative of charge, is going to be the same as velocity, which is the derivative of position. A potential difference, delta V, acts the same as a force in a mechanical system. And resistance, R, is the same as B, our viscous damping coefficient that we talked about in resistive forces last semester. Capacitance acts like a spring constant, and it's actually 1 over the spring constant. And inductance plays the same role as mass. So if I were to look at, say, the time rate of change of current, that's the second derivative of the charge, that would be the same as acceleration. The energy in an inductor is 1/2 Li squared. Well, the kinetic energy of a moving object is 1/2 mv squared. Remember, L goes like m, and I goes like v. And the energy in the capacitor is 1/2 Q squared over C, which is the same as the potential energy stored in the spring. Since Q squared goes like x squared, and C goes like 1 over K. And the rate at which energy is lost, I squared R, is the same as the rate of energy lost due to friction, BV squared, that we talked about last semester. So then that RLC circuit differential equation that we looked at, L times the second derivative of Q with respect to 0, plus R dQ dt, plus Q over C equals 0, is exactly the same as the damped object on a spring, where you have the forces, MA, and the forces are minus KX and minus BV. So let's look at an RLC circuit. In the figure we have a resistance, inductor, and a capacitor with values given. Calculate the frequency of damped oscillation, and what would be the critical resistance. So the frequency of damped oscillation is just 1 over LC minus R over 2L squared. Take the square root of that. We plug in the values that are given, and we get 1.58 times 10 to the 4th radians per second. Or if we wanted to know in terms of frequency and not angular frequency, it's omega over 2 pi, be 2.51 kilohertz. The critical resistance of the system is going to be the square root of 4L over C. We plug that in, the critical resistance would be 69.9 ohms. So if our resistor was a little bit more, we would have a critically damped system. So to review what we talked about today, we talked about LC circuits and how that's like a mass on a spring and the charge will oscillate back and forth on the capacitor. Then we also talked about RLC circuits, which are similar to a damped oscillator mechanically.